Okay, guys, we're going to talk about the fourth way of calculating delta H today. The fourth way is called using the standard enthalpy of formation and using data tables in order to figure out what delta H is. So we've been talking about delta H and how to calculate it. We've done 3 of them so far. What are the ways we now know how to calculate delta H? What are they? Stoichiometry, calorimetry, and Hess's law. Now we're going to use some data tables and figure out what delta H is, but it's really using this thing called standard enthalpy of formation. So please be following along here in your chapter 4 guided notes as we go through these slides, and we'll learn this stuff. It's not that bad. Okay, so Hess's law is much more useful if you know lots of equations. So now that we know Hess's law, we can use it and use a lot of equations, and we can figure out what delta H is for almost anything. Okay? There's this thing called standard enthalpy of formation. Remember what enthalpy, what's the symbol for enthalpy, guys? Yeah, it's capital H. What does it mean? It means the heat energy either absorbed or released in a chemical reaction. And we usually talk about it in terms of change in enthalpy. So we're looking at how enthalpy changes as the reaction proceeds. So standard enthalpy of formation. It's given this symbol right here, okay? The standard part is denoted with this little, it's called a naught sign. It looks like degrees. So this means that it's in standard conditions, and we'll talk about that in a second. And the formation part is given by this little subscript F. And so look for that today. The standard enthalpy of formation symbol looks like this. Okay, but here's the definition. It is the enthalpy that is required for the formation of 1 mole of a compound from its elements in the standard states. And the units that are given for standard enthalpy of formation are kilojoules per mole. Okay, standard states are when you have these conditions. You're at 1 atmosphere of pressure, which is atmospheric pressure most of the time, right around there. 1 molar concentrations, and the temperature is 25 degrees Celsius, which is about room temperature. So that's why they call it standard states. If you were going to go to a lab and do a chemical reaction, most likely you're going to be really close to standard states. Okay, for an element, the enthalpy of formation, the standard enthalpy of formation for an element is what? Is 0. Okay? So we'll remember that today. And you'll see that on your data tables that if you look up just an element, it's going to be 0. Okay, standard enthalpy of formation, you need to be able to write the equations for standard enthalpy of formations. So let's do that. This one says, what is the equation for the formation of nitrogen dioxide? What elements, guys, are making nitrogen dioxide? Nitrogen, if you're going to make it from the elements, you'd have to have some nitrogen and have to have some what? Some oxygen. Okay, now if we go back to the definition of standard enthalpy of formation, we're going to form 1 mole of the product. And so here's what that would look like. Let's explain it. So we need to form 1 mole of this. That's important. Standard enthalpy of formation is when we form 1 mole of that substance. So 1 mole is going to be the product. There it is. How would you make it from the elements? Well, you need nitrogen and you need oxygen, just like you guys said. But if we're going to form just 1 mole, nitrogen and oxygen are diatomic. So you see a little 1/2 here for the moles. You're going to use 1/2 moles of nitrogen. And 1/2 of N2, how many nitrogens would we have? Just 1. If you take half of 2, you just get 1, and so that's why you see a 1/2 sign there. You can see that in enthalpy of formation equations all the time, where moles is given as a fraction. Okay, that gives us 1 nitrogen, and then you would have to add 1 mole of oxygen to that nitrogen to make nitrogen dioxide. Okay? So again, these standard enthalpy of formations is when you make 1 mole of that substance. You have to make 1 mole to meet the definition. Now let's try this again. I want you guys to write the equation for the formation of methanol. Okay? CH3OH. What elements would we need in order to make methanol? Carbon, hydrogen, and oxygen. So let's see if you guys can write the formation reaction here for methanol from the elements. Okay, so try it. Okay, let's see how you did. Remember, by definition, we want to make 1 mole of methanol. So I always start these equations or these reactions by writing the product here, methanol. So CH3OH. And I need to make 1 mole. So make sure that you remember that. Okay, now let's make it from the elements. We need carbon, don't we, guys? So I'm going to put carbon here. Is carbon a diatomic element? It's not. So I need carbon. What other elements do I need in order to make methanol? Hydrogen. Is it a diatomic element? It is. So when you write hydrogen, you can't just keep it as H. It's always going to be H2 in its elemental form. And what other element do I need? Oxygen. Okay? So I'm going to have oxygen. But is it diatomic? It is diatomic, so we got to remember to put a little subscript 2. Now we're pretty much done. That's what makes methanol. But are we balanced? We're not. And so, are we balanced in terms of the carbons? We are. What about, how many hydrogens do I have? 4. So I need 4. How do I get 4? I'm going to have to react 2 moles of hydrogen. Now this is the tricky part. Oxygen. How many oxygens do I have in the product side? Just 1. But on the reactant side I have 2. So yeah, we can use fractions here and put a 1/2 right there, or 0.5. If you want to put it as a decimal, that's fine too. And this would be our enthalpy of our standard enthalpy of reaction equation for making methanol from the elements. Okay. And here's the good thing about figuring this out. Chemists have already done this, and they've already determined the delta H values, the delta H of formations, the standard enthalpy of formation, for a lot of substances using this. From the elements, what is the delta H value for this substance? And they've done that for almost everything. And they've listed them on a nice thermodynamic data table for us to use. And so I think I've got, and so we did get that one right. I've got a little bit of information to help you see how they organized it. Okay? So this is the thermodynamic data table that I gave you at the beginning of class. And it says here that you can look up the delta H of formation for the substances on your data table. Where do you see methanol? And I think that the phase here is going to be very important. What phase were we in? The liquid phase. So if we looked up the delta H value for that reaction, what would it be here? Good. Here's where we see the methanol. And delta H of formation is given in this first column, the standard enthalpy of formation. And for methanol in a liquid form, now notice that there's different forms here. There's gas, there's liquid, and so keep track of that. Our delta H for that reaction is going to be a negative 238.7. And what are my units? Kilojoules per mole. And so that's why it was important that we keep the product side, that substance, as 1 mole, because that's how many kilojoules of heat are released in 1 mole of methanol being formed from the elements. Does that make sense, guys? Okay. So stay with me. We're going to use this information to figure out the delta H for reactions. Not just a substance, but we're going to put them into a chemical reaction and be able to determine the delta H of the reaction. Okay, so since we can manipulate the equations, we can use the heat of formations to figure out heat of the reaction. Like I was saying there. Let's do it with this equation. Okay, I've just got an example here. And I hope that this is making sense, but if we have this reaction, and I wanted to figure out its delta H value for the whole reaction. So for the whole reaction, I want to know what its delta H value is. Well, we can use the delta as standard enthalpy formations for all of these substances here and calculate it through one big equation. So let me see if I can help you understand what we're doing here. So if you look at an energy diagram, okay, where it puts delta H on the y-axis and it puts reaction time as it proceeds on the x-axis. Okay, we're going to start here with some reactants. Okay, so my reactants are going to start here, and we've got C2H5OH plus 3 O2s. Okay, well, there's going to be some kind of activation energy where you see this hill, and then it's going to, if it's exothermic, it's going to come down, and the products, which is going to be the CO2, the 2 CO2s, plus the 3 H2Os, are going to be down here somewhere. Okay? How would you calculate delta H? Well, you would look to where the products are, and then you look at where the reactant started. How do you calculate delta H, guys? How do you calculate it? Final, good. Final minus initial. So the final was the products, right? So we're going to take the products minus the initial, or the reactants, I guess I should say. Isn't it products minus the reactants? That's what delta H is equal to. And in this case, is delta H going to be positive or negative? If you take the products, let's just put some numbers to it. Let's just make it easy. This was 10 and this was 20. So if we take the products, 10, minus the reactants, the initial, what are we going to get? A negative 10. So we went down, so it's, delta H would be negative. So let's use that, kind of keep that idea there, of products minus reactants. And when we use this equation, we're going to try to figure out the delta H for this whole reaction using the enthalpies of formation, the standard enthalpies of formation. So if I could look up the standard enthalpy of formation for CO2, so let's see if we can do this. The delta H of this reaction is equal to, could I look up the delta H of formation, the standard enthalpy of formation for CO2 on those data tables? Couldn't I do that? But I would have to times that number by the coefficient here, which is the number of moles. Okay, and then I would add, because the standard enthalpy of formation is for 1 mole. This says I end up with 2 moles, so I'm going to times that by 2. We're going to add in the standard enthalpy of formation for H2O. But what would I need to times it by? 3. Okay, if I took that and added them together, wouldn't this be the products? Okay, and when we do delta H of the reaction, we need products. What do we have to do to the reactants? Subtract them. So I'm going to put in a negative sign here. Okay, and now let's go to the reactant side. And so we could calculate the delta H of formation, the standard enthalpy formation for C2H5OH. But we would have to times that value in your data table by what? By 1. So I'm just going to keep it as a 1 there. And let's add in the standard enthalpy of formation for this substance, which is oxygen. But I would have to times that value by what? by 3 because I have 3 moles, and in the data tables it's just for 1 mole. Okay? If I did that and came up with this equation right here, would that essentially use the standard enthalpy formation of the products minus the reactants? Wouldn't that be what I'm doing? And I could go, the products minus the reactants, and I can calculate delta H for this reaction. Okay? And that's exactly what we're going to do. And I've got a couple of practice problems to go through to help us remember this. This is a huge equation. Okay? We're going to go through and try to remember how to remember that. So, okay, so let's see what we got here. So the standard heat of formation for many different substances are listed in your thermodynamic data tables. It lists them in alphabetical order with what element starts the substance or the compound. So aluminum, it's just starting with A, and then it just goes in alphabetical order. So if you're looking something up and it's a compound, look at what it starts with. Then go to that part in the alphabet and you've got it. And remember, we're just considering this first column here. We'll talk about what delta G and what S is later in the chapter, but we're just concerned about that first column. So when we look up values, we're going to look them up like that. Okay, so how I learned this equation when I was going through chemistry, my teacher called it the Big Mama equation. Okay, so in your notes, you're supposed to write down the Big Mama equation. And here's what I want you to write down. Okay, right here. Okay, the delta H of the reaction under standard conditions, which again is 25 degrees Celsius, 1 molar, and 1 atmosphere of pressure. Okay, it's got to be under those conditions. But we can figure out the delta H for this reaction. It's equal to, and you see this weird sign right here. This is a Greek letter, sigma. It means take the sum of. So sigma times N sub P times the delta H of formation of the products. So again, that's sigma, which means take the sum of. N means the number of moles times the delta H of formation, which you will get from the data tables, of all of the products here. So this sigma sign, if there's more than one product, you're going to add them together because the sigma sign means take the sum of. Okay, so once you do that for all the products, we're going to subtract. Then you see the sigma sign again, which means take the sum of N sub R, which means the moles of the reactants, times the delta H of formation of all of the reactants. Okay. So the symbol sigma, it means take the sum of the terms. N sub P and N sub R represents the moles of each product and reactant. So NP is moles of the product, and R is moles of the reactant. And you will get those numbers, those moles, from a balanced chemical reaction. So, I mean, you can see why it's called the Big Mama equation. There's a lot to it. There's a lot to it. But we're going to go through a couple of practice problems, and I think it will make sense. But I think it's kind of helpful to remember the general term. The delta H for the reaction is equal to the delta H of the products minus the delta H of the reactants. Okay, we're always going to keep the product, you're going to list the products first, then minus off the reactants, and that's how you find delta H. Okay, some things to remember. The delta H of formation, the enthalpy of formation for elements is what? Yeah, if it's just an element, it's going to be 0, and it will show you on the data table as well that it's 0, but it's always helpful to remember that it's 0. Okay, let's do a couple of practice problems. Practice problem number 21 says, using your standard enthalpy of formation table, which is your thermodynamic data tables that I gave you, calculate the delta H of the reaction for the following chemical reaction. Okay, look at this thing. So we've got 4 moles of ammonia in the gas state, 7 moles of oxygen in the gas state, and we make 4 moles of nitrogen dioxide in the gas state and 6 moles of water in the liquid state. Now, phases will matter. So this G means gas, this is gas, and this is liquid. It does change, you'll notice. Okay, so let's write down the Big Mama equation first, which said that delta H of the reaction is equal to sigma N of the products times the delta H of formation of the products minus sigma, the number of moles of the reactants, times the delta H of formation of the reactants. Okay, so we're going to keep that form. This is called the Big Mama equation. Let's use it now and plug into it. Okay, so what are we going to start with? Reactants or products? Yeah, let's start with the products first. That's what we list first. Okay, the sigma sign says we're going to take the sum of the number of moles times the enthalpy of formation for the products. So here's how we do that. I always like to start it off with a big bracket symbol. Okay? Because we're going to put brackets around the products and we'll put brackets around the reactants so we can keep our orders of operations in line. Okay, now let's start with the product side, which is over here. Let's just start with the first one. How many moles of NO2 do I have? We have 4, so I'm going to take 4. Now let's look up nitrogen dioxide gas. Let's look up the delta H of formation in the data tables for nitrogen dioxide. Okay, so it's going to be listed under N. It's alphabetical order. And remember, it's just that first column there. What is it in the nitrogen dioxide gas? 33.2. So positive 33.2. And notice that's kilojoules per mole. So that's why we had to times it by 4 here, because I have 4 moles in my equation. Okay, so we're going to close that off. Now the sigma sign means you take the sum of. And we have more products, so I'm going to put a plus sign here. So we're going to take the sum, which means addition. And we're going to add that to, how many moles of water do I have? 6. Okay, now let's look up what the enthalpy of formation for water in the liquid phase is. So it's water, so it starts with H, so I would look under the H for hydrogen. And remember, it's in the liquid phase. What do you guys get for that? Yeah, it's negative 285.8. Okay, we'll close that off. We times it by 6 because there's 6 moles of it in my equation. Okay? Are there any more products now, guys? No. So I'm going to close that off with a bracket symbol. Now, let's keep going with our Big Mama equation. What do we need to do? So it's products minus the reactants. So now let's put a minus sign in. I always like to put another bracket symbol here when we start the reactants. So I throw in a bracket symbol. N, what does that stand for? The number of moles, right? So of my reactants, let's go over here. I've got 4 moles of NH3, so I'm going to put a 4 right here. Now let's look up what the enthalpy of formation is for this NH3 molecule. So ammonia in the gas phase. It starts with an N, so I would look under the N in your tables. So NH3 gas, what is it, guys? Are you getting a negative 46.1? Yeah. Negative 46.1. We'll close that off with a parentheses there. And sigma, guys, so we see the sigma sign right here, means take the sum up. Do I have more reactants than just that? Yeah, so we're going to add it. That's what sigma means, taking the addition of it. How many moles of O2? 7. So put that there. And now I've got O2, which is oxygen. So it's going to be listed under O for oxygen. Guys, is that an element?
Yes.
It is. So what should it be? It should be 0. And what is it? What is 0? Okay, so 7 times 0, well, that's 0, but I'm still going to put it in there anyway. And close it off with another bracket symbol. Okay. Now we have a math equation that we can work with. Okay, let's simplify what's here first in these brackets. Then we're going to minus off whatever's in this bracket. Okay, so let's grab a calculator. So 4 times 33.2 is 132.8. But we're going to add that to 6 times a negative 285.8. And that's a negative 1714.8. Okay, let's keep going. We're going to minus off 4 times a negative 46.1, which is a negative 184.4. Now, what's 7 times 0? Well, it's just 0, so I'm just going to leave it off. Okay, so now let's simplify what's in this bracket. So 132.8 minus 1714.8. And so I get a negative 1,582. That's what that equals. Minus, okay, now what's happening here? We got a minus. Guys, what do we do if we have a minus? Yeah, this minus times a minus and a minus is a positive, right? So let's take a minus 1,582 plus 184.4. What does that give us? Did you guys get negative 1,397.6?
Yeah.
Okay, so my delta H, I'm running out of room there, so I'm going to write it over here. My delta H for this reaction is equal to a negative 1,397.6. What are my units going to be? Yeah, in the data tables it says it's kilojoules, and so that's my units, and that's my answer. Guys, is this reaction going to be endo or exothermic? That is exothermic. Yeah, the delta H is going down. So if you were to draw the energy diagram, it would look something like this. Okay, it's releasing 1,397.6 kilojoules of heat to the surroundings. So heat is leaving. Okay. So just another way to find delta H. Big Mama equation, there's a lot to it, right? But can we do this, guys? I think you guys can do this. I've got another practice problem for us to try. So did we get that one right? Negative 1,398. Yeah, if you rounded this 0.6 up, so if you just rounded this 0.6 up, that would be an 8. So, okay, good job. We got it right. I've got one more practice problem, and I'd like you guys to try this one on your own. Okay? So again, determine the delta H of this reaction using the Big Mama equation and your thermodynamic data tables. Let me give you a second to try that one. So please try it on your own, get an answer, and then hit play and see if you got it right. Okay, guys, let's see how you did with this one. So I'm not going to rewrite the Big Mama equation, but if you wanted to, you could rewrite it. And I would recommend, actually, let's do that. So the delta H of the reaction is equal to bracket the number of moles of product. Well, forgot my sigma sign here. The sigma, the number of moles of product, times the delta H of formation of the products, minus the sigma sign of the number of moles of reactants times the delta H of formation of your reactants. And so there's our Big Mama equation. Let's just follow that. And I'm going to start with, so delta H of the reaction is equal to, I'm going to start with the products because that's what it wants me to do. So I'm looking over here and I've got 1 mole. So 1 mole of aluminum oxide. It starts with aluminum, so I would, in your data tables, look under A. And it's aluminum oxide, and so delta H of formation for that substance is a negative 1,675.7 kilojoules. Okay? And what this sigma sign means is we're going to take the sum of the products. So I'm going to add that to my other product here. I've got 2 moles, so I'm going to times it by 2. And we've got Fe. That seems like an element, but let's check it. And what is the delta H of elements, guys?
0.
Yeah, it should be 0. But if you ever are curious, iron, if you look it up, it does say 0. Okay? So you can save yourself some time if you just remember that the element's delta H of formation is going to be 0. So I'm going to put that in there. Now that's all of my products. So I'm going to close it off with a bracket sign. Now, in between the products and the reactants, I've got to minus it. Okay, so I'm going to put a minus sign, start another bracket. Now we're doing the reactants. So I'm coming over here. I've got 2 moles of aluminum. So I'm going to put 2 moles. Now, is aluminum an element, guys? Yeah, so what should its delta H of formation be? 0. We could look it up, but if you do look it up, it does say 0, right? Okay. So let's save ourselves some time. Let's just remember that it's 0. Now the sigma sign means we're going to take the sum of the reactants. So let's add the other reactant in here. I've got 1 mole of this compound, iron oxide. So Fe2O3, which is a solid. So it starts with, well, it's Fe, but it's for iron. So I would look under I on your tables. Fe2O3. Okay, Fe2O3 solid. Did you guys get a negative 824.2 kilojoules? Okay. And that's all of my reactants, so I'm going to close that off with the bracket sign there. And now it's just a math equation. Let's see if we can simplify it as fast as we can here. So delta H of reaction is equal to, this is going to be, well, 1 times that, so a negative 1,675.7 plus 2 times 0 is 0, so that's, I'm just going to leave that off, minus 2 times 0 again is 0, and 1 times negative 824.2 is that one. Okay, now we get to this point, and again we have a minus, a minus. So what does that mean, guys? That means plus. Whenever you have a minus, you add. And so we're going to add 824.2. So let's see what that is. A negative 1,675.7. Add 824.2. Did you guys get a negative 851.5?
Yeah.
Okay. So my delta H of reaction is equal to a negative 851.5. What's my units going to be? Kilojoules. Good. Kilojoules. Endo or exothermic, guys? That's exothermic. Yeah, it's delta H value is negative, which means we're releasing heat to the surroundings. That's exothermic. So just another way to figure and calculate delta H. So now we've got 4 ways, right? We can use our thermodynamic data tables, use the Big Mama equation. I hope that this makes sense, but I know it's something it's kind of complicated and it takes a little while to learn. So to help you, I have a worksheet in your student workbook. It's titled Enthalpy of Formation Worksheet. So please go there now. This will give you some more practice on doing these types of problems and see if we can't get a few more right before we move on. Again, it's called Enthalpy of Formation Worksheet, so please go there now and try it, and hopefully this video helped.